Sir, you are not audible.
Okay. Now I'm audible.
Yes, sir.
Okay, I think this Google Meet is updated. Okay, I think they completely changed that interface, right? Okay. So now the sine PWM technique we are discussing for single phase inverter, sine PWM technique for single phase inverter. So here in single phase you have two different techniques. One is unipolar and bipolar. Unipolar and bipolar. In case of three phase, so there is nothing like unipolar and bipolar, so it is always unipolar. Okay, in three phase it is always unipolar. So this is single phase inverter. We have this DC source. This DC source is represented with a large capacitor of infinite size. A large capacitor of infinite size. Similarly, this is simply a DC source. So its voltage is VD. Okay. So now we want to calculate this output voltage VAB. So that is VAB. So this VAB can be calculated by using this terminal voltages A phase and this negative DC bus voltage. We discussed it, right? This is positive DC bus and this is negative DC bus. Okay. So this VAB is VAN minus VBN, right? VAN minus VBN. So VAN, so when S1 and S2 are turned on, when S1 and S2 switches are turned on, so VAN is plus VS. When S3, S4 are turned on, so VAN is minus VS, right? Similarly, BN is also changes, right? Okay, so in case these two PWM methods, one is unipolar and bipolar PWM methods. So first we'll discuss bipolar PWM. You already discussed this, right? You might have studied this, right? In case of bipolar PWM, sine PWM, you require a sinusoidal waveform. You require a sinusoidal waveform of this one. So this will be the reference waveform. So this is your reference waveform or modulating signal. And you have carrier signal. So this is carrier signal. You have this carrier signal and carrier we've selected as triangle signal. It's a triangle carrier signal, right? So here we already discussed in previous class MA and MF. MA and MF both we discussed, right? So MA is amplitude modulation index, MF is frequency modulation index. So this MA is to control the output voltage, whereas this MF is to control the harmonic spectrum or quality of output voltage of the inverter, right? So here this MF I have given is 15, right? So that means, for example, if I consider so 50Hz signal is the modulating waveform, right? This is the modulating waveform. So then the corresponding carrier frequency is 15 into 50. So that comes out to be 750 Hz, right? So this is the carrier
Excuse
frequency.
Me, sir.
Yes.
Can you please repeat MA and MF part?
MA we discussed in previous class, right? This MA
Yes.
is amplitude modulation index. MF is frequency modulation index. So this MA we defined as the peak value of reference signal, right? The peak value of reference signal by the peak value of this carrier signal. Okay, the peak value of carrier signal. So in this case, if you notice that the carrier signals are varying from +1 to -1. Carrier signals are varying from +1 to -1. But the modulating signal, so this is not touching, right? This value is not 1, right? It's somewhere maybe at 0.8 or 0.9, right? So here this MA is maybe around 0.8 or 0.9. Okay. So that means whatever the output you are getting, with full MA equal to 1. So that means with MA equal to 0.8, the output is 0.8 times what you will get with corresponding to MA equal to 1. Okay. Similarly, this MF, we will discuss this one in the next slide. So what is the purpose of this MF? Clear? So here, in case of bipolar, you require one triangle carrier and one modulating signal, that is one sine wave, right? So here, this one will control this S1, S2, right, and S3, S4. The firing signals for S1 and S2 and S3, S4 both are same. Okay. So here, you know this triangle carrier comparison, right? You might have studied in BTech. Okay, so here this reference waveform is compared with the triangle waveform. So when it is greater than the means when the carrier is greater than the modulating signal, so upper switch may be on. So when it is less than the modulating signal, the bottom switch is on, right? Or in other words, in one case you will get positive voltage, in other case you will get negative voltage. Okay, so in case of this one, in case of this, right, so here, so these are the switches corresponding to when it is greater than 1. So these are switches corresponding to S1, S2, and this is corresponding to S3, S4. Clear? So these are switches corresponding to S1, S2, and S3, S4. In case of bipolar, right, in case of bipolar, the firing signal for S1 and S2 both are same, and similarly S3 and S4 are same. So S1 equal to S2, the firing signal. In other words, it is gate signal, right? So this is S3, S4. So both are same, and these two are complementary, Clear? So in case of this one, right, when S1 and S1 is on, right, when S1 is on, what is the voltage? VAN. What is the voltage VAN when S1 is on?
VD.
Voltage is VD, right? So that is plus VD here. Okay. Similarly, when S1, S2, in case of same thing, S2 is on, right? So that means what is the means S3 is off, right? So at the same time, what is the voltage? So here, what is the voltage? It is 0, right? So these VAN and VBN, so both are complementary, right? This VAN and VBN, so both are complementary. So therefore, you will get the complementary output voltage between VAN and VBN. So if you want to calculate this VAB, so VAB is the difference between VAN and VBN, right? VAB is the difference between VAN and VBN. So here this value is 0. Okay, here this value is 0, but at the same time its value is plus VD. Okay, so therefore the difference is VAN minus VBN. VAN is 0 and VBN is minus VD. So therefore overall voltage is, this is minus VD. Okay, similarly at this case, so this is plus VD, whereas here its voltage is 0. So therefore you will get plus VD. So that means this waveform is changes from plus VD to minus VD. In other words, it's changing from the full DC source voltage to minus VDs, and there is no zero level. No zero level. The output voltage directly jumps from plus VD to minus VD, and similarly minus VD to plus VD. Clear? Okay. You have any doubts on this?
No, sir.
Okay, you are already studied this, right? This bipolar, you might have studied this. Okay. So next, its corresponding harmonic spectrum of this waveform. The harmonic spectrum, we'll get back to this one later. So next we will discuss unipolar PWM. unipolar PWM. So in case of unipolar PWM, you have four switches, right? S1, S2, and you have switch S3, S4. You have four switches, right? S1, S2, and S3, S4. So in case of unipolar PWM, you require two carrier, one modulating signal, right? So this is one arrangement, or two modulating signal and one carrier. Okay, you require two carriers and one modulating signal, or two modulating signal, one carrier. So the performance of these two are same, these two are identical. So when you are considering the two modulating signal or two carriers, so those two must be in opposite direction, right? It must be 180-degree phase shift, right? So this is, I considered two modulating signal and one carrier signal, two modulating signal and one carrier. So here this is the first modulating signal, and this is the second modulating signal, so which is phase opposite to the first one, right? This is phase opposite to the first one. Clear? So you have this triangle carrier. So here also I consider MF equal to 15 Hz. So that is carrier frequency is 750 Hz. Carrier frequency is 750 Hz per 50 Hz cycle. Okay, so here there are two modulating signals. For example, this is considered, so modulating signal 1. So this is 1, and consider this is 2, the second modulating signal. Right. So here the modulating signal 1 is control the switches S1 and S4. The modulating signal 1 is control switches S1 and S4, and similarly the modulating signal 2 will control S3 and S2. Okay, so this is controlled by modulating signal 1, and this is controlled by modulating signal 2. So in case of bipolar, you have this same thing, right? S2, switch S3, S4. So you have only one modulating signal, so that is controlled by these two, and another one is controlled by these two. Clear? So this S3 and S4 in case of bipolar. Okay. So in case of unipolar, so this S1 and S2 is controlled by one modulating signal. This S2 and S3 is controlled by another modulating signal. So that means each phase leg, you have two legs, right? Each phase leg is controlled by an individual modulating signal. So that modulating signals are mirror image, right? So now,
Excuse
so this
me,
one,
sir.
yes,
Sir, in bipolar there is only one modulating signal, sir.
yes, one modulating signal.
Sir, that one modulating signal will control S1 and S2.
Yeah, S1 and S2. That means S1 and firing signal for S1 and S2 both are same. Okay,
Yes, sir.
so when it is above the modulating signal, the S1 and S2 are set to 1. So when it is below the modulating signal, S3 and S4 are set to 1. Sorry, 0. Okay, so likewise it is controlled.
Yes,
Got
sir.
it?
Yes, sir.
The firing signal for S1 and S2 are same, right? When you see simple logic, right? When you have one carrier and one modulating signal, right? There is two chances, right? Whether the modulating signal is greater than the carrier signal or lesser than the carrier signal, right? So that means at a time you can control two switches. If you have one modulating signal and one carrier signal, so you can control two switches, right? So when it is right, so in case of bipolar, the switches for S1 and S2 are same. Similarly, S3 and S4 are same, right? So this is controlled. S1 is controlled. So when modulating signal, maybe when modulating signal is greater than this carrier. In case of this one, so when modulating signal is less than carrier. Likewise, okay,
Yes, sir.
right. In this case, you have two modulating signal, right? So that means one phase leg, so S1 and S4 are controlled with one modulating signal, and S2 and S3 are controlled with another modulating signal. So each phase leg is controlled by an individual modulating signal, right? So let us consider, I think, yeah, just a moment. Right. Right. So now observe here. So this is the modulating signal. So now observe here. So this is the modulating signal, right? And this modulating signal, we are already assumed that. So this will control the phase leg S1 and S4, right? S1 and S4. So this is, so now we have seen that these are the intersecting point, right? So this is one intersecting point and this is another intersecting point, right? These are the intersecting points, right? So these two are intersecting points. So therefore, so when it is modulating signal is greater than the carrier signal, so then a pulse is generated. So this is the corresponding pulse for the switch S1, right? So this is the corresponding pulse for the switch S1. Okay. Similarly, I'm not shown here the firing pulse for the S4. So firing pulse for the S4 is complementary to this S1, right? So that means at that time that S4 is completely 0. Clear? Is clear? Right. So here, these are the interaction of this modulating signal 1 and the carrier signal. So it generates a firing pulse here. Similarly, the same thing, modulating signal 2. So this is modulating signal 2. So this is modulating signal 2. So here, so these are the intersecting points with this modulating signal. So these are the intersecting points. So with this modulating signal. So this modulating signal is supposed to generate the firing signal for S3 and S2, right? So this is the firing pulse S3. So at the same time, S3 and S2 are complementary, right? Therefore, S2 will be 0 at that time. Clear?
But sir, here is carrier signal is greater than modulation signal.
So negative, right? Which is more negative here? Which is more negative? So this is negative, right? So this is also negative, right? So it is, for example, this is +1, so -1. So it may be -0.5, right? So means obviously it is greater than that, right?
Okay, sir.
Clear?
Okay.
So these are on the negative side, right? So these are on the positive side and these are the which is more negative. So that is important, right?
Okay, sir.
Okay. So this is firing pulses we are generated by intersecting the two modulating signal. Two modulating signal we have generated the firing pulses. So now this is the firing signal S1, right? So here this is S1. The corresponding VIN is this. Agree? So this is upper switch is on in one phase leg. So this is the corresponding output voltage, right? So this output voltage is generated for this one. Clear? This output voltage is generated with this, right? Similarly, this VBN, so this is generated from this firing pulse, right? It's clear?
Sir, actually, what will
So if
happen? Like
S3
we
is
are,
on, this output voltage is plus V.
so
Yeah.
sir, actually, what will happen? We are actually taking a gate pulse for third switch, sir. But we are going to complement like the other 180 degree. I mean, The other part will be switching on S2, right, sir? In unipolar.
No, no.
Sir, actually, we
See,
are
see, we
giving
are
a gate.
measuring this VAN, right? I will.
Sir,
Yeah,
okay,
we'll
sir.
see.
What happens? What will happen if we take this as a
No, no.
gate pulse?
See here, sir. See here. See here. Just see here. So
Yes,
this S1 is on, right here.
yes, sir.
Okay.
Yes,
We
sir.
are controlling the switch S1 and we are controlling the switch S3, right?
Yes,
Okay.
sir. Yes, sir. Yes,
Okay.
sir.
So we are measuring the voltage between A and N, right?
Yes, sir.
We are measuring the voltage between A and N, right? So we are already discussed that when S1 is on, so S4 when this is on, so this is off, right? When this is on, this is off, right?
Yes, sir.
Okay. Then
Yes, sir.
S1 is on, S4 is off, S3 is on, S3 is off. So S1 is on, right? So what is
Yes,
the
sir.
voltage between these two voltages?
That
VAN,
VD.
this VD, right?
Yes, sir.
Okay. Similarly, when S3 is on,
Yes, sir.
right? What is the voltage? This is also
Minus.
VD, right?
Uh,
Agree? Why minus VD? It's plus VD only, right? See here, there is no minus VD here, right? Either it may be VD or it may be 0. Okay. When this bottom switch is on, right? When
yes.
this S4 is on, so what is the voltage? It is 0.
Okay,
Okay.
sir.
There is no minus here, right?
Okay, sir.
So here there is no minus here. So we already discussed, right? This terminal voltage is having two labels, only plus VD or 0.
Okay, sir. Okay, sir. Okay, sir.
Okay. So now we require VAB, right? So this VAB is VAN minus VBN.
Yes, sir.
Is clear?
Yes, sir.
Okay.
Okay, sir.
The same thing we're analyzing here. So this is when S1 is on here, right? So when this is on, this gate pulse is on. So this is its corresponding output voltage. This is its corresponding output voltage, and this is its corresponding output voltage when S3 is on. Okay.
Okay, sir. Okay, sir.
We're not interested in this one, right? So now the rest of the pulses are like this, right? This is S1 is on, S3 is off, S1 is on, and S3 is off, right? So why, if you notice that these pulses are become narrower, right? So why it is narrower? You can observe here. See here, this intersecting points is very small, right? So here, this intersecting point is very small, right? So therefore, the pulses will become narrower. Okay. So here, these pulses are narrower. So whereas these pulses are wider. Clear? So when come to this side in the negative half cycle, so here these pulses are wider, whereas here these pulses are narrower, right? So here you produced a narrow pulse. So whereas here this wide pulse here. Okay. This is the natural behavior of the sine wave. This is due to the natural behavior of the sine wave, right? So now we are subtracting these two, so VAN and VBN. So if you notice that, so here this is betterly visualize it, right? So here this is one big pulse, right? You have this pulse. Okay, you have this pulse, and you need to subtract this pulse from here, right? Agree? We need to subtract this VBN from VAN, right? So there the difference is, this is the difference, and this is the difference, right? So here these two pulses, when you're subtracting, so this split into two pulses. This is another one, this is one pulse, and this is another pulse. Okay, the simple logic, right? So one pulse is some bigger and another pulse is some narrower, right? So therefore, if you subtract these two, so you will get something like this, right? You will get two pulses. Agree? Okay, you got it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, same thing here you can observe, right? So this is a wider pulse, this is a wider pulse, and this is narrower pulse, right? So if you subtract this one, so this one split into 2. Right? So here, if you notice that, I will, if you notice that in the positive half cycle, the width of this V1 or the width of the switch S1 is higher when compared to the switch S3. Okay. In positive half cycle, the widths are more in upper switch, that is S1 gate signal. So here these widths are more, right? These widths are more when compared to this, right? These widths are more, that means S1 and S4, these widths are more when compared to this one. So whereas in the negative half cycle, these widths are narrower when compared to this. So S1 is narrower in negative half cycle and S3 is wider. In case of positive half cycle, S1 is wider with pulses when compared to S3. So that means in that case, so in positive half cycle, you will get complete positive voltage. Positive half cycle, you will get complete positive half cycle, and negative half cycle, you will get complete negative voltage. Clear? Is clear?
Yes, sir.
You understand this? Okay. In case of here negative half cycle, the negative is more dominant. In this, see here, simple logic, you are subtracting this one and this one, right? In case of positive, this is VAB, right? In case of positive half cycle, so this is more dominating when compared to this one. So therefore, the output voltage is positive. In case of negative half cycle, this VBN is more dominating. So therefore, you are getting the negative voltage. Clear? See here, this one I circled. See here, this is narrower pulse and this is wider pulse. So therefore, negative side is wider pulse. So therefore, the output, effective output is negative. Clear? In case of bipolar, the output voltage is plus Vs, directly jumps from plus Vd to minus Vd or plus Vs to minus Vs. See here, in same positive half cycle, you have this change from plus Vs to minus Vs. So, but you notice that, right? If you notice that this one, right? So this is positive half cycle, right? The positive portions, and these are the negative portions. So this positive portion is more when compared to this negative portions, right? So here this positive widths are more when compared to this negative width. So this effectively, so this is positive. Effectively, this is positive. Similarly, on the other side, so here these are narrower. So these are narrower and these are wider. So therefore, effectively, so this is negative. Okay. It looks like this waveform is changing from plus Vs to Vs, a normal square waveform. So, but actually, positive half cycle, the voltage is more dominant. That means positive voltage is dominant in positive half cycle, and negative half cycle, negative voltage is dominant, right? So here it is effectively it is positive, and whereas here it is effectively negative. Okay. The drawback here is it's
Sir, I have a
positive,
query.
right? In positive, yeah.
Why we are getting the
Go ahead.
wider thing in the other side, sir?
See here, from these waveforms only we are getting this, right? So here, so when the waveform is moving like this, right? So this become narrower, right? That means this pulse is narrower. So obviously this pulse is also narrower, right?
Okay, sir.
Okay. So therefore these pulses will become wider. So when negative pulse on bottom pulse are become wider, this output voltage will become wider, right? Okay. So therefore, the correspondingly, you'll get the negative pulse, negative voltage. Okay. The difference is, okay. See, the one thing I want to emphasize is that, so this waveform is clear. It looked like a AC waveform, right? Okay. this waveform is look like a AC waveform. Normally AC waveform, positive half cycle you have positive, negative half cycle you have negative, right? So you have positive here, and in the negative half cycle you have negative, right? So here this waveform is nowhere close to AC waveform, right? This waveform is nowhere close to AC waveform, but if you carefully observe that, so here this positive half cycle is dominating with positive, a bigger pulse, negative half cycle is dominant with negative, bigger pulse. That's it, right? Okay. So here only thing it changes from plus PS2 or plus full voltage to minus full voltage, that is plus VD to minus VD. So whereas here you have this intermediate voltage VD to 0 and minus VD. Okay. So this is line voltage, right? Or the phase voltage, or between in between phases A and B, right? Okay. The same thing, right? The same thing, unipolar PWM with MF equal to 15, with MF equal to 15, but the difference is here you have only one modulating signal. Here you have one modulating signal, but two carrier signals. Okay, but two carrier signals, but those two carriers are in opposite direction. Those two carriers are in opposite direction. So that means one carrier will control, for example, this carrier is to control the switches S1. So whereas this other carrier, which is 180 degrees shifted, right, this one, so this is used to control the other phase leg, right? The effect is same, or output and everything is same, right? The effect, that means the output voltage, there is no change in the output voltage. So if you calculate, if you count these pulses, right, so these pulses are around 15. If you count this one, so these pulses are 15. So if MF equal to 15, right, so here the number of pulses is also 15, right? 15 pulses in the pulse stops, you can count it, right? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, right? So you will get 15 pulses. Similarly, on the negative half cycle, you will get 15 pulses. So whereas here, right, if you count these pulses, so this is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, right? So this entire pulses are 15. Okay, friends, in case of bipolar, right, in case of bipolar, the pulse that produced in one cycle is equal to MF, equal to MF. So whereas in case of unipolar, so that is equal to 2MF. In case of unipolar, equal to 2MF. Okay, provided so this MA is less than or equal to 1. We'll discuss this. Okay, you got it? Okay, so here in case of bipolar, so it is the number of pulses are MF. So in case of unipolar, so it is 2MF. Okay, in case of unipolar, it is 2MF. It's clear? So now we move forward to harmonic spectrums. So this is bipolar harmonic spectrum. So this is bipolar harmonic spectrum. So this is corresponding to MF equal to 15, corresponding to MF equal to 15. So here the switching frequency, or this MF, this means the pulses are MF pulses are generated, right? So therefore, so this is corresponding to MF. You have harmonic, right? You have harmonic at MF. You have harmonic at MF, but you don't have harmonic at 2MF. Similarly, you have harmonic at 3MF, and you have no harmonic at 4MF. So here harmonic is present in MF, so no harmonic at 2MF, and 3MF you have harmonic, and 4MF you have no harmonic, right? So that means for even multiple of harmonics, or MF, so you have no harmonic. For a hard multiple, you have harmonic. So these small harmonics are there, right? MF plus or minus 2 is there, right? So these are known as sideband harmonics. So these are known as sideband harmonics. These are known as sideband harmonics. These are known as sideband harmonics. See here, similarly here, these are sideband harmonic. There is no harmonic here, but the sideband harmonics are centered here, right? Similarly at MF, 3MF, you have these two sideband harmonics. So here it will be like this. Okay. So this is the harmonic spectrum corresponding to MF equal to 15. Okay. So when you are increasing the value of MF, so for example, if you are increasing the value of MF, this waveform is shifted, right? This harmonic spectrum is shifted to higher ordered harmonic side, right? So therefore, normally, so when you are practically, we'll consider up to 49th order harmonic. Okay. Normally, in machines or anything in power systems or machines, right? We normally consider up to 49th order harmonic. So whatever harmonic greater than 49th order harmonic, so we assume that the magnitude is very small and it can be easily filtered out by using the machine inductance or the transformer or transmission system in impedance. Okay. Harmonics, right? You have this inductance. For example, you know these basics, right? Harmonics, for example, uh, you're directly fed an harmonic which is of 15th order harmonic to a machine. 15th order harmonic to a machine, right? So machine having some inductance, right? Machine is having some inductance. So normally inductance is omega L, right? So omega L is 2 pi F into L. In case of 15th order harmonic, so this F is, I will write here. So machine inductance, if you assume this is L, right? So overall inductance, there is omega L, right? It is 2 pi F into L. So for example, if you consider F is the 15th order harmonic, so here, so it should be 2 pi into 15 F into L. So that is 30 times pi FL, right? So that means the effective impedance that is offered to the machine to this 15th order harmonic is increased by 15 times, right? That means it is effectively increase the machine harmonic that is offered to that, right? So therefore, so these harmonics and can easily filter out by the machine impedance or machine inductance. We will discuss this in later classes in detail. Okay. So now come to our actual discussion. So this is harmonics are centered at MF to MFN, right? So therefore, so it can be something like this. Some K times MF plus or minus K times MF plus or minus some maybe some X, right? So these harmonics are in this order K times MF plus or minus X. Okay. So this X will be odd number. This X will be odd number in case of MF. In case of K, okay, I will. So I will open again. Okay. Right. So I will write like this. So it is P times MF plus or minus this X. Right. So here this P is this MF. This is P. This is X. Right. So here this X is 2. So here this X is 1. This 3. Right. So that means harmonics are very like this. Is MF. So harmonics you are getting is MF plus 2 MF and MF minus 2. Right. In case of 2MF, so it will be MF plus or minus 1 and plus or minus 3. So 2MF. Okay. So simple example, for example, if I consider equal to 15, right, you have harmonic at 15th and you have harmonic at 13th and you have 17th order harmonic. So from this, your 13th order harmonic, 15th order harmonic and 17th order harmonic. So whereas here you have no harmonic at 30th, there is no harmonic at 30th, and you have harmonic at 29th order harmonic, 31st order harmonic, and you have this 27th order harmonic and 33rd order harmonic. Got it? Got this? Similarly here at MF, 3MF, you have harmonic. At 3MF, you have harmonic. At 3MF, you have harmonic at 3MF. And correspondingly, 3MF plus or minus 2, you have harmonic. And 3MF plus or minus, you have these harmonics, right? Similarly, 4MF, at 4MF, you have no harmonic. At 4MF, you have no harmonic. And you have harmonic at 4MF plus or minus 1, plus or minus 3, and plus or minus 5.
Sir, hello.
Yeah, go ahead.
Sir, on what basis we decide that the frequency of order this are present, like ms plus 2, ms plus 2, 3ms plus 2?
So this is
On
HF
what basis?
spectrum that what we obtained. Yeah, this is why HF spectrum what we obtained by decompose this waveform. Okay. By using fast Fourier series or double Fourier series, if you decompose this one, so this is the spectrum you will get. Okay.
Okay.
Similarly, we did for square wave and quasi square wave, right? In square wave, we try to draw these, right? So these are the complicated one. So by using this double Fourier series, you can analyze this harmonic spectrum, or by using some simulation, maybe using MATLAB, you can simulate this. Okay.
Okay, sir. Okay.
Hello, sir. Another doubt, sir.
Yeah.
Sir, is there any pattern to take values of P and X, sir, in that PMX plus RF?
Yeah, I will discuss that. Okay, I will discuss now. Okay, so you have this PMF plus or minus X, right? So this X will be odd number. So this X will be odd number in case of so this X will be odd number, right? So this is even number, right? So in case here this is even number, right? So here in case of P is, if P is even number, so this X will be odd number. Okay, you can see here, right? You need to use some analytical approach. So this MF, right? This is first MF, right? So here this corresponding to P is 1, right? So here this P is 1, right? So therefore, so here you will get even numbers. So that means if P is odd number, in that case X is even number. Okay, right? And one more thing, if P is even number, in that case this effective value is 0. That means effective. So that means at At PMF, so this harmonic is 0. Okay, it's clear?
Yes, sir.
PMF plus or minus x is odd number, so this P will be even number, and this P is odd number, x will be even number, right? At every time, so if this PMF, that means if MF equal to 15, right, corresponding to 2MF, that is 30th order harmonic, 60th order harmonics, so all these will be not present. Yeah, what's your doubt? What's your doubt?
Sir, I have a doubt.
Yeah.
Hello. So these
Yeah, go
harmonic
ahead.
2MF plus plus or minus 1, 2MF plus or minus 3, are these non-existent?
Or adjacent only, right?
Sorry?
These are adjacent only, right? These
Okay.
are present.
Okay, okay.
Okay.
Yeah.
Only the 30th means that PMF is not present. That PMF is not present when P is even. Okay.
Yeah, okay.
The PMF order harmonic is not present when P is even. Right.
Even.
Clear. So why we are doing all this analysis, right? Okay. So for example, I consider MF equal to, I will okay. So we already discussed that we have harmonic at 15th order harmonic, 13th, 17th, and we have no harmonic at 30, and we have harmonic at 29, 27, 31, and 33, and so on, right? So for suppose if you select, this is for if you select MF equal to 15, so that is 75 H carrier, right? Okay. For someone, for example, someone is selected MF equal to 16, or for example, someone is selected MF equal to 20, that is 1 kHz carrier, right? Someone is selected 1 kHz carrier because it's easy, right? 1 kHz carrier, it's easy to pronounce rather than 750H, right? Some round figure. Okay, so now we will see what is the drawbacks if we select 1 kHz carrier. So corresponding to this N, MF will be 20, right? Agree? MF is 20,
Yes, sir.
right?
Yes.
Yes, sir.
So what are
Yes,
the
sir.
order of harmonics you will get? Corresponding to MF, you have harmonic, right? 20th order harmonic, you have, right? See here, this here 15th order harmonic, MF you are selected 15, you have harmonic at 15, right? Similarly, you have harmonic at 20, and you have harmonic at 18, right? So MF minus 2, right? MF minus 2 and MF plus 2, right? So that means you have harmonic at 18 and 22. Agree? So this is, if for example, this is corresponding to 20, so this will be 18 and this will be 22. Agree?
But sir, MF
Sir.
is
Right.
even here.
Yes.
Similarly, you have no harmonic at 40, right? Here you have no harmonic at 40, but you have, right, but you have harmonic at, so where it is 2MF plus or minus 1 and 2MF plus or minus 3. 2MF plus or minus 1 is you have harmonic at 39,
41.
okay, you have harmonic at 41, and you have harmonic at 37 and 43.
43.
That is 37 and 43, right? Okay, but you don't have harmonic at 40. Similarly, for 3MF, you have harmonic at 60, you have harmonic at 60, and you have harmonic at 58, 56. Similarly, you have harmonic at 62 and 64. Clear? Is clear?
Sir,
Yes, sir.
Yeah. Go
Sir,
ahead.
there is one doubt, sir. If MF is even, sir, then harmonic will exist, na, sir?
MF is even.
Then harmonic will exist. But
Harmonics
if
are exist at what,
P is even,
where it
then
is exist.
sir, if MF
No,
is
then
even,
P is
then
even. See, here this PMF, right? Okay. If
yes,
this
sir.
P is even, okay. So in that case, you
Yes,
have no harmonic at this PMF harmonics, whatever the harmonics that are related to this PMF, right? So that all are 0. Okay.
yes, sir.
So
Yes, sir.
here this MF2, this is this 40th is 0. Okay.
Yes, yes,
Similarly,
sir.
this 80th harmonic also 0. This 80th harmonic, so that is corresponding to 4MF, right? So this
Yes, I got
80th
it, sir.
harmonic is this corresponding to 4MF, that is 0, right? So if you compare these two, so one case, one side you have MF equal to 15, on the other side we have MF equal to 20. Okay. So if you compare
Yes, sir.
these, so all these MF equal to 15, all these are odd numbers, right?
Yes, sir.
Okay. So we have 13, 15, 17, 27, 29, 31, and 33. So all these are odd numbers. So whereas here, if I select MF equal to 20, we have this 18th order harmonic 20, 22, right? Again 56, 58, 60, 62, and 64. All these are even number. That means it's a mix of even and odd. Okay.
Yes, sir.
Predominantly, right. So it is even numbers are predominant, right? So normally you are aware of that, right? When you have even order harmonic, so there is just some DC component, right? That means the waveform is not quarter wave symmetry. There is just some DC component. At any cost, we need to avoid even order harmonics, right? At any cost, we need to avoid even order harmonics, right? So therefore, so when you select the carrier frequency as 1 kilohertz, so this even order harmonic problem will be adjusted, right? So therefore, instead of selecting 1000 or 1 kilohertz, right, you may select 950 hertz or you may select 1050 hertz. Clear? So this is corresponding to MF equal to 20. 1000 hertz is corresponding to MF. This one is MF is 19, right? So whereas here this is 21. Is clear? So when you are using a bipolar sine PWM technique, right? When you are using a bipolar sine PWM technique, so it is always preferred to use MF as odd number. Okay, MF as odd number, so that the in harmonic spectrum, these even order harmonics will be eliminated. Okay, so that is the point you need to remember. Clear? So you have,
Okay, sir.
stop here. You have any doubts on this? You have any doubts on this? Please ask me if you have any questions or queries.
So it is possible to generate two modulating signal of opposite phases. So this
Yeah, it's possible, right? It is possible.
sure.
It is
Okay,
possible to generate two opposite signals, right? By using, we have inverter signals are there, right? By using that inverter signals, you can generate two modulating signals, means two opposite signals. You may have studied that op amps, you might have studied inverting op amps, right? Okay. I mean hardware, when you're when you're using hardware, by using inverters, means op amp signal, inverted op amps are there, right? That means one, it is the polarity of the output signal. Okay. So by using that, you can do that. Okay. So digitally, it is also possible, right? Digitally, it is easy, right? You have multiply with -1 with the actual signal, you will get a negative signal, means opposite signal of that, right? Sine wave is normal signal, right? If you want opposite, you just multiply with -1. Digitally, it is easy. When you are actually implemented analog, right, you can easily generate that output signal. One simple way is you just interchange the terminals. Okay. If you interchange the terminals, obviously the polarity will be changed, right? Okay.
okay.
Clear?
I have a doubt, sir.
Yeah.
Suppose if it is 6 MF, The X will be up to plus or minus 7. Yeah, 6 MF.
If it is 6 MF, right? Okay.
Then it will be
At
plus
6
or minus.
MF,
Then it will be plus or minus 7.
so you don't have harmonic. Yeah, 6 MF you don't have at 6 MF you don't have harmonic, right? But you have harmonics at 6 MF plus or minus 1, 3, 5, and 7.
7.
Okay.
Yeah. Okay.
1, 3, 5, 6 MF minus 1 plus or minus 3 plus or minus 5 and plus or minus 7. Okay. So normally we are not that much interested to go beyond 6 MF, 7 MF. So normally we are more emphasize on MF, 2 MF, and 3 MF. That's it. Okay. Okay. So once you can use this, so later means you can easily extend to higher levels. Right? You have any other doubts on this? So only thing we have to remember is when you are implemented bipolar sine PWM techniques, the MF should be odd number. Okay. Right. Instead, if you directly, for example, if you select only one kilohertz carrier frequency, right? So that means in that case you will get the problem of getting even order harmonics. To avoid that, you must choose MF, which is a odd number. Clear? Any other doubts you have?
So,
You have any other doubts?
so out of these unipolar and bipolar, uh, do they have their separate
Yeah.
applications or we have to select the better one?
We have to select the better one, right? Okay. So normally, if you are observing that, right? So unipolar is better one, right? Okay. We'll discuss that in later class. Next class we will discuss that. Okay. When you're comparing this unipolar and bipolar, okay, we'll discuss in the next class. Okay.
Okay, sir.
So both are having their own advantages. Okay. So normally unipolar is preferred. So we'll discuss that why it is preferred. Clear?
Sir, using same system, we can generate unipolar, bipolar, both.
No. For the procedure is different, right? Unipolar, the procedure is different, and bipolar, the procedure is different, right? Okay. So only thing you can share that carrier and modulating signal.
Okay, sir.
Okay. If you have any other doubts?
No, sir.
No, sir.
Okay. Fine. Okay. I'm stopping here.
Thank you, sir.
Thank you, sir.